So the reason in ASCII that everything is 8 bits is because it started out with this idea of let's have 7 bits and we'll encode so we'll have 128 values and that's all we need, and so each combination is going to represent a different value, right? These are going to represent A through Z, and these are going to represent capital A through Z, right? Each of these will represent a different value because we said we're going to have 128 values, so we'll just simply, for each of these combinations, just put that in. To compress things, we're going to kind of look at it backwards, which says, here's the characters we have, let's come up with bit combinations for them, rather than saying, here's bit combinations, let's assign each value a bit combination. We're going to, rather than saying, hey, let's go ahead and we've generated these bit combinations and we'll just simply put values in everywhere. We're going to figure out for each value what is the best bit combination to do. And the idea behind this is that not all these characters are of equal importance. I mean, they're of equal importance getting your message across, but they don't occur nearly as often, right? So the premise behind Huffman encoding is that rather than giving everything the same length, and notice I've been switching between 7 and 8, it's because, right, we can only really encode some, we can only really access things in terms of bytes, so these would really take up 8 bits, even though we use 7. The idea here is that we are going to give more frequent characters less bits. So E, because it occurs really, really frequently, will use up less bits. It might get a shorter sequence. So when we see it, it's going to take up less space. Whereas these less common characters like Z or X, they're going to be longer bit length, but fortunately not take up nearly as much space. And then we don't encode anything we don't use. So this means that we'll be creating a unique encoding for every single document that we encode and decode, but we can just then, but that's fine. That's fine. That's just extra time on our part. Okay? So the idea here is that we are going to use 2 structures to build this. We are going to use a binary tree, not a binary search tree, and we're going to use a priority queue. Okay. So and the way this is going to work is, suppose we want to send some document, some compressed document. We want to take this document and we want to send it in a compressed format. How will we do that? Well, given a document, I will create an encoding for it, and I'll send the table that you used to decode it, the table that I used to encode it, and I will, I'll generate that table, this encoding table or encoding tree, and then I'll send the table and the encoded message, and then the recipient uses the same table to decode what they just got, right? So it's kind of like an encryption. It's kind of like encrypting something, only you intend the recipient to be able to break it, okay? And this is based off of frequencies. So again, we need to limit our discussion. I'm only going to be talking about English here, mainly because it's easy and I only have to deal with 26 characters, and punctuation then, right? Other languages are going to be a lot more difficult because how many unique characters does Japanese have? And the answer is, I'm not really sure, but you've got 50 hiragana characters, 50 katakana characters, and then you've got as many kanji as you can lay your hand on, at least 2,000 official kanji, possibly 20,000 unofficial kanji. So it ends up, that's a lot more symbols than English. So we're just going to stick with English because that ends up making our discussion a lot easier. All right. And we're going to be just dealing with lowercase letters and spaces and punctuation. In fact, we can rule out the punctuation in general. So every language has what we call a frequency fingerprint or a frequency table. Frequency, here we go, letter of frequency, right? And it's actually pretty interesting to look at, right? But the idea here is that we could, in English, right, these letters appear at a relative frequency, okay? And E is the most common letter, followed by T, followed by A, followed by O. Ito and Shurlaku is kind of the way that it was thought of, this old typography thing. although it was Ito and Sherdlu because they thought C appeared less often than it actually did. But Itoin, right? These are the most common characters. E occurs 12% of the time. Well, sorry, most common letters. Space is actually the most common character, right? Because every word is followed by a space. So the idea here is that we'll give the most common characters or letters a much smaller encoding so that they'll occur, so that they use up less space, and then things like this will use up more space.